Section 3.2 we were working on last time. We had talked about relative extrema, and if you'll remember, the way we find a relative extreme point is that we take the derivative and we set it equal to 0 or set it equal to a place where it potentially doesn't exist. So usually that would happen like if you had a numerator and denominator kind of issue going on maybe. And then what we do is we create something like a sign chart. That's what you see down here. For those of you who were here last time, you remember seeing these here. And we picked points between them. I called them test points. And you can pick any point you want between them, and you just test them. And you test them into what? Do you remember? The derivative, right. You test them into the derivative graph, and the derivative graph tells you if it's positive, then it means the original graph's increasing. If the derivative is negative, then the original graph is decreasing. Okay, so that's what we had looked at. We looked at a couple of examples last time. We talked a little bit about graphing technology to be able to sort of determine from the picture point of view what you can do. And then we ended on this very last one where I showed you that you can do it without the technology as well, and it would have looked like this. This particular one didn't ask for that, but we talked about the fact that it certainly could have, and it wouldn't have been any crazy thing to do that part of it. All right, we're going to talk about another kind of extrema next. Our next kind of extrema is called an absolute extrema. So absolute extrema is the actual biggest value on the entire graph, or smallest value on the entire graph. Obviously not all graphs have this, right? If a graph were to look, say, something like this, it wouldn't have an absolute extrema because it continues going up and down forever. But if you had a graph something like this, it would have a location where it had an absolute smallest value. On this graph, it would be the vertex of the parabola down here. And you may have some graph where it has multiple peaks and valleys, so maybe it does something like this. So in this case, you have several points that are relative extrema, right? Everywhere there's a max and min, you have a location where a relative extreme point exists. But there is only one point that's an absolute minimum on this one. Now, the other thing that can happen when you're looking for absolute extrema is that you restrict the window that you're looking in. So instead of looking at the entire graph, you look at the entire graph on an interval, like only between -5 and 5, or something like that. So if you took, say, for instance, I'll do this first graph that I picked over here. If you took this graph right like this, and it was restricted to this interval, that is, it starts right here, and it stops right here, so it's a constricted view. You only have that portion of the graph. Then you'll always have the absolute max and the absolute min. In this case, the absolute minimum is right here. It's actually an end point. And the absolute maximum would be right here, which is actually a relative, high point. Okay, it's a location where there's a relative extrema. So the extreme value theorem is exactly what I was talking about there in this last picture. It says that if we have a continuous function, it's defined on a closed bounded interval. So it has endpoints and we restrict the viewing. We only look at a portion of the graph. Then it will attain both an absolute maximum and an absolute minimum on that interval. And this graph right here is exactly a picture of what's happening in that particular description. So the absolute max is on an endpoint in this case. The absolute min is on an endpoint in this case, and the absolute max is actually at one of the relative extreme points. So it could be at either thing, a relative extreme point or at an endpoint. All right, so given that information, what that means is that we have to test two kinds of points. We have to test the critical points. Okay, critical points, remember, are the places where the derivative is equal to 0 and we solve it. So we have to test those critical points, those places where we have relative extreme values. And then we have to test the end points as well. And if you only test one or the other, you're very likely to have excluded the actual answer. And you have no way of knowing unless you test all of these kinds of points. Now, obviously, you only have two end points, right? They're set. But you may have multiple maxes and mins in between, so the relative extrema might be more than one or two. I mean, it's possible. So these are the kinds of points that we're going to test. And we're going to do an example that shows how it works. So does everybody have this part written down? Okay. All right. So here's an example of a graph. This is the graph of 3 cosine x. So ignoring the interval, tell me what you know about this graph from trig. Say again? Almost. It won't be 1 and -1 on this one, actually, because, yeah, it has a 3 in front. But you're right, it keeps going up and down, right? And then the 3 in front means it'll be the 3 and -3 instead of the normal 1 and -1, absolutely. So very good. So if we were actually looking on the entire interval, it has infinitely many relative maximums and infinitely many relative minimums, right? It's just going to keep bopping up and down the entire time. Make sense? So if we're actually wanting to find the relative extreme points, that would be cumbersome, because we'd have to have some way of writing them, and you've learned ways in trig of writing them where you found all of the maximum points, or when you did it in trig, you probably found something like all of the x-intercepts, right? That's where you, and it looks something like, maybe not for this particular one, but it looks something like pi over 2 plus k pi, where k is an integer. Does that sort of sound familiar? It's a little cumbersome to write, not real helpful to look at least. It looks a little awkward. So what we're going to do in this problem then is we're going to restrict the window we're looking at. We are only looking between pi halves and 5 pi over 4. That's it. Everybody good with that so far? That may include a maximum, like one of these peaks. It may include a minimum. It may include neither one. Okay, it doesn't have to include everything that's in the graph, or it may include one or the other. So the first thing we're going to do, and we're going to do it in the order that I listed on this previous slide, is we're going to find the relative extrema on the interval. Okay? So relative extrema means to take the graph that we're given, or the equation of the graph we're given, and find the derivative. So what is the derivative of 3 cosine of x? Excellent. -3 sine of x. All right. And then what do we do when we find the derivative to find relative extrema? Right. Set it equal to 0. So if we set this equal to 0, the -3 doesn't actually affect the problem. Agreed? Okay. So this is really the same thing as having sine of x equal to 0. So I'd like for you to think about your unit circle graph, right, for sine. Where does the sine value equal 0 on your unit circle? At 0? Where else? And pi? And 2 pi, and we could go to the negatives as well, right? I mean, this description continues in both directions, because we could also use negative pi and negative 2 pi. We don't really want all those values. We only want the values that are between pi halves and 5 pi over 4. So which, if any, of those values are between pi halves and 5 pi over 4? Pi is the only one, isn't it? So the only value that we care about is the value that's on the interval we're looking in. So this is the only one that matters on our interval. There we go. So what do? Well, we don't need to do a sign chart. We don't need to do maxes and mins from a sign chart. What we really want to find out is the absolute extreme value. Well, how do you figure out, if you're given several points, how do you figure out which one's the biggest value among those points on a graph when we refer to it that way? You can look at the graph. What are you looking for if you're looking at the graph, though? We haven't talked about concavity yet, so hold tight for a sec on that. Okay, but what about just the points? If there's just points that you're given, and there's no graph here except for just points, how do you decide which one of those points is the absolute extrema? Which one's the absolute maximum point? Which one's the absolute minimum point? What do you look at? We'll put them on axes so it makes sense. What do you look at? Yeah, the one that's highest up, right? So whichever one right here, this would be our maximum. And this one, actually, the way I've drawn it, looks like I have 2 minimum. Right? So the one that's highest up, but the highest up one, that was really very mathematical right there, highest up one. The highest up one, what can you tell me about its values? What is it about its ordered pair that tells you it's the highest up one? Has the biggest y value, right? So what we're looking for as we look at these values that we're about to look for is we're looking for which one has the biggest or smallest y value. Does that make sense? That's what it means to be an absolute extrema. It means it has the biggest or smallest y value. Or you could say, in this case, since we're dealing with a function g of x value, right, because that's y. So what do? Well, we take the point that we just looked at, which said it was pi, and we actually evaluate the value of pi into the original equation g of x. So we're doing g of pi, which is 3 cosine of pi. And what is the value at pi for this equation? It's -3. Cosine of pi is -1, right? Mm-hmm. Do you have a question, Darby?
Why did you cross out, what was the one after pi?
It was 2 pi, and I crossed both of them out because they weren't in this interval. Mm-hmm. Yeah, the only one that I wanted to do was the one that was, or the ones, if there were more than one, that happened to be in the interval. Yeah. So this is sort of like part A. This is the relative extrema, or the relative test points, the relative points. Part B is to test the end points. So right now, the fact that I've done part A doesn't tell me yet anything about the graph. It really doesn't. I could still have an end point giving me the same kind of information or giving me other information that makes part A irrelevant to the rest of the actual question. So the second thing I have to do is to test my end points. And I always have 2 end points given. Okay? So the first end point that I'm given is at pi halves. So I'm going to test g of pi halves. So that is, I'm going to test 3 cosine of pi halves. So what is that value going to be? That one's 0, because the cosine of pi over 2 is 0. And then the other point that I need to test is g of 5 pi over 4. So we need 3 cosine of 5 pi over 4. Anybody remember what the cosine of 5 pi over 4 is? It's going to be a root 2 over 2. And you have to decide is it going to be positive or negative. It's negative because I'm in quadrant 2. Cosine values are negative in quadrant 2. So the 3 is already there, and then I have negative square root 2 over 2. So this is negative 3 square root 2 over 2. And if you want to write down in addition to this, not in exclusion of this, like I want the real answer written down, but if you want to write yourself a decimal approximation so you can compare them easier, that would be fine. What is 3 square root 2 over 2 approximately? Okay, so roughly negative 2.12. Is that okay for everybody? So what I want to do then is that I want to look at these 3 y values. And I want you to tell me, those 3 that are squared in red now, which one is the biggest? Oddly enough, it's 0, right? Because it's the only one that's not negative. So this right here tells me that that's my maximum, and I'm going to write it out properly in a moment. Which one is my smallest? Negative 3. So this one is my minimum. So what do I say? Well, my answer is that I have an absolute, and I'll abbreviate it ABS, an absolute minimum at pi negative 3, right? The x value is pi, the y value is negative 3. And I have an absolute maximum at pi halves 0. And that's the answer you give when you're done. And you have to test both the endpoints and the relative extrema to get both those pieces of information. Any questions on that one? Okay, one more question we're going to look at, slightly different. This is one of those ones where I've told you before, your graph may not look exactly like my graph because we have some flexibility in the information that we're given. But it gives us some conditions or some details about a graph, and then we have to sketch a graph that matches up with those details. So some of the things that we sketch are going to match with each other, and some things might not. So the directions say sketch a graph of the function with the following characteristics. It has an absolute maximum of 3. This is the y value they're giving you. It's going to be on only the interval of -2 to 2. So somewhere between -2 and 2, it's going to have that maximum value. And then it also tells you that the absolute minimum does not exist. So this is telling you that this is true for the whole graph. All right, so somebody tell me something guaranteed that has to show up on your graph based on the information they gave you. Yeah, that absolute maximum 3. I'm going to have something up here at y = 3. Agreed? Now, it does not tell me what value it has to be at from the x perspective, does it? I mean, it doesn't say at x = 2, or at x = -2, or even at x = -1. We get to pick. So here's the interval I'm looking at between -2 and 2. Somewhere in between -2 and 2, you need to put a point at a height of y = 3. Okay? So, Emily, where did you put your point?
1.
At 1. Did somebody else pick 1? You did, Edgar? Okay. What about something else? What else did you guys pick?
0.
At 0. That would work too. I'll put mine at -1 just to show that I can be different than you. All right, so there's my point. What else does it tell me? There's no minimum. So what does it mean for a graph to have no minimum? That would be no maximum that you just drew. Yeah, it needs to somehow, it could be a parabola, but at least some portion of the graph has to keep going down forever. Like it wouldn't have to be both sides. So this is the picture that Kaylee was drawing in the air, something like this. Does that sort of act, okay, that would work, right? But does it have to be all of that? No, you could just have this piece right here. That'd work too. You could even have it coming down here and then going back up over here. That'd be fine. It doesn't tell you that it has an absolute maximum on the entire graph. It just tells you it has an absolute maximum between -2 and 2. So you have lots of options. Mine actually looks like this one that Kaylee said. You have lots of options about how it could look, but there are some features that have to be there. You have to have a point at 3, and in a local area around it, it better be going down, right? If it's going to be a relative extrema. The other option is you could have something where you used an end point. Like you could have this particular point right here, and it looking like that. So between -2 and 2, that's my absolute maximum value. Absolutely is, right? There is no minimum because I've got this piece of the graph going down. And the other side, I can do whatever I want with it. So that would be another option. Lots of choices on how this could be drawn. Any questions on this one?